So continuity. A preference relation is continuous if it's preserved under limits. So for any sequence, let's say xn, yn, okay, let's assume this is a sequence, and it goes on from n equal to 1 to infinity. Let's assume that the first element of the sequence, the x, is always preferred to y, and this is for all elements of the sequence, so for all n. So the idea here of continuity is that consumer preferences cannot jump. So if we have the sequence of bundles in which in each pair the first element is preferred to the second, as we have here, then as the sequence converges, so we take higher and higher elements in the sequence, there is some limit bundle. If there is some limit bundle in such a sequence, then the limit bundle has to have the same relation. So the first element must also be preferred to the second element. So the preference between the elements of a sequence of commodity bundles basically carries to the point of convergence at the limit. And the preference ranking cannot be reversed at the limit of the sequence. So if we consider the bundle X, and this bundle is the limit bundle of x of n as n approaches to infinity, and y is the limit bundle for y as n approaches to infinity, then if the preference relation that we have here, if this preference relation is continuous, then we must have x at least as good as y. So when we look at the ranking here, it is preserved at the limit, right? It's the same ranking. The first element at the limit is also preferred to the second element of the sequence at the limit. The classical example of preferences that are not continuous is that of lexicographic preferences. Now, you may be familiar with this. In case you're not, quick reminder. Lexicographic preferences look to the first element or the first commodity in the bundle in order to rank two bundles. So here, if I want to decide what my ranking here is, I have to compare the first element, x1 and y1. If x1 is greater than y1, I stop here, I look no further. The second element is irrelevant, and I will say that x is strictly preferred to y. If the other way around, if y1 is greater than x1, then y will be preferred to x. If they're the same, now I turn to the second element in each bundle and I compare those. And it's the same thing. If x2 is greater than y2, then x will be preferred to y. And vice versa, if y2 is greater than x2, then y will be preferred to x. And if they're the same, if x2 is equal to y2, those two bundles are actually identical. If I had three commodities here, I would keep going, by the way. And I would look to the third element in each bundle, and I would compare them in the same way. So this ranking thing, the dictionary, by the way, right? So this is how words in the dictionary are ranked. The reason that the word answer, for example, is found before the word apple in the dictionary, okay, is because they both begin with the same letter A, but the letter N is found before the letter P. The reason that the word apple, in turn, is found before the word bath is because the letter A of apple comes before the letter B of bath. And it's irrelevant that the second letter here, A, comes before the second letter P. All that matters here for the ranking is the first letter. So what's very interesting here with this preference relation, is that no two different bundles are ever in the same and different set. I'm always able to rank. And this is why, by the way, this is used in the dictionary, right? There is one unique ordering of words. If given two words, I will always be able to say which word comes before. So I'm able to look for these words in the dictionary in a way that is convenient. So what's interesting about lexicographic preferences is that they are not continuous. Why are they not continuous? So let me give you a sequence. Okay, consider these two bundle. So xn is 1 over n and 0. Yn is 0, 1. Now for all at n, xn will be strictly preferred to yn. Okay, so all elements here in that sequence, the first entry is preferred to the second entry. And the reason for that is that this number here, no matter how great n is, 1 over n will always be greater than 0. Right? And so here this x1 will always be greater than y1. And so x is always preferred to y. Okay, but what happens at the limit? So at the limit of xn as n approaches infinity is 0, 0, 0. Right? The limit of 1 over n as n approaches infinity is 0. And the limit of y as n approaches infinity doesn't change. The bundle doesn't change. It's still 0, 1. So at the limit, what can I say here? Well, y will be preferred to x. Why is that? The first entry will be the same, 0, and the second entry here, 1, is greater than 0. So at the limit, I have y strictly preferred to x. So the bundle is not preserved. At the limit bundles, if you like, do not have the same relation. The preference relation is reversed at the limit of the sequence, and this is precisely what we do not allow in a continuous preference relation. Just a concluding thought, by the way, the reason that we want to impose this continuity property is that we want to be able to draw indifference surfaces. We want to be able to say that two different bundles, that we are indifferent, right? And with the lexicographic preference relation, you can see that no two bundles are ever found on the same indifferent surface. Each indifferent surface is its own bundle. So the space is partitioned into indifferent surfaces that are just points, bundles, right? And I'm not able ever to draw an actual line, an actual indifferent surface. So that's the reason for imposing this continuity preference relation on this continuity property on the preference relation. So another way to think about this, why is the continuity requirement so important? When you're looking at lexicographic preferences or non-continuous preferences, you have a space here. This is commodity 1, commodity 2, and let's pick a bundle. For example, X has certain quantity consumed for commodity 1 and quantity consumed for commodity 2. And I am unable to find any other bundle in the space which is such that this other bundle would be on the same indifferent surface as X, right? Each bundle is its own indifference surface. So I could think of the space here with, an infinity of points everywhere in the space. Each point is a bundle, and I am able for each bundle to rank. If I'm given bundles, I'm always able to tell which one is preferred to which, right? That's the whole point of lexicographic preferences. A ranking always exists. But there are no indifferent surfaces. Now that's a problem for utility representation, because when I build a utility representation, I look at all the indifferent surfaces in the space, right? Assuming that they exist. And then what I do is I assign a utility level to each indifferent surface. And I can do this by constructing some kind of ray from the origin, for example, like this. It doesn't even have to be a straight line, right? But the ray will intercept each indifferent surface at a particular... I'll be able to assign for each indifferent surface a real number, right? And that real number will be its utility level. And there are an infinite number of utility levels, right? That's an order, a particular order of infinite. And this is how I can rank all such indifferent surfaces. When I'm looking at lexicographic preferences and these indifferent surfaces do not exist, okay, so I've removed these indifferent surfaces, I'm able to rank really all the bundles which are located on this ray, and I will continue forever, right? I can provide a ranking, it'll go on forever. Each bundle on this ray is assigned a real number, but I'm unable to cover the whole space because it's a question of order of infinity. The space itself is R2, and when I'm constructing the utility function with array, I'm in R. So we have different orders of infinity, and the existence of indifferent surfaces is how you get from R2, from a space in R2 or Rn in a more general case, to a representation in R, the real numbers, a real valued function.